Hi, it's Valentine from Simplistic. Today we're going to take a look at this problem where we have an equation given to us. CHCl3 plus Cl2 gives you CCl4 plus HCl. And the initial rate of the reaction is measured at several different concentrations of the reactants with the following results. So I'm going to just write down out here, that's trial 1, that's trial 2, that's trial 3, and that's trial 4. All right. Okay, so we have this data that's given to us from the problem, and essentially the first thing we need to understand is they've given us the concentrations of the two reactants. So you have the concentration of CHCl3 and then the concentration of Cl2, and they've given you the initial rate of the reaction. And so for every trial they've given us specific concentrations and specific rates. And what the problem wants us to do is it wants us to use the data provided to us to calculate the rate law for the reaction, the rate constant for the reaction, and finally the overall order of the reaction. So in order to do this, first of all, we need to write the general expression for the rate law, okay? So the general expression for the rate law can be written as rate is equal to the rate constant K times the first reactant raised to some power x, we don't know what that is, we'll find that out, times the second reactant Cl2 raised to some power y. And we need to determine what x is and what y is, okay, to find the order of the reaction. Now, to find the rate law of the reaction, we essentially have to determine x and y and then essentially plug them in out here, and then this entire thing would become the rate law of the reaction with the values for x and y known. The rate constant for the reaction, so once we determine x and y, excuse me, we know what rate is, we know what this and this is, we can solve for the k, okay? And finally, for the overall order of the reaction, we just add x and y together, and that gives us the overall order of the reaction. Now, this reaction has a few different steps, so I would recommend pausing the video from time to time just to kind of absorb things. And I'm going to jump to another page as we work through the problem. And so you might want to take a screenshot of the problem so that you can keep track of what's happening in each trial. All right. All right. So let's get to it. Okay. So using the rate, so the first thing we want to do is to determine the rate law of the reaction, which is this. The first thing we want to do is we want to basically take trial 1 and trial 2, okay? And we're going to write out the rate for each of the trials, and then we'll put the corresponding values for the concentrations of each of the reactants in the rate law, okay? So let's go ahead and do trial 1. I'm just going to call that T1. So for trial 1, the rate is given to us as 0.0035. And I'm gonna, to make things easier, I'm just gonna eliminate the units for now so that we don't have to write too much. So we have 0.0035 is equal to the concentration of CHCl3, which is, is equal to K. So we're gonna write the K out there. Concentration of CHCl3, which is 0.010 raised to a power x, times concentration of Cl2, which is this, raised to a power y. All right, so that's trial 1. In trial 2, what happens is we have 0.0069, which is this, times the respective concentrations raised to the powers of x and y. So we still write the K out there. Respective concentration of CHCl3 is 0.020 raised to x times the concentration of Cl2. Notice carefully, the concentration of Cl2 did not change in trial 2, okay? So that's going to stay the same. And that's crucial to understand, okay? And the reason for that is because in order for us to solve for x, we need to cancel out the y's. So you want to choose the trials where one of the reactants is actually, where the concentration is actually staying constant. That way you can cancel out the y term, okay? All right, so now the easiest way to go about this is to, the easiest way to go about this is to divide both the reactions. Okay, so when you divide both the reactions, what you end up getting is we're gonna immediately the k's cancel out, and then all the y terms cancel out, and then we're gonna simplify. So I'm just gonna slide this over slightly, and if you divide, so the left side of the equation becomes 0.5072, and then the right side, the top term remains the same. Let's keep that the same. And then the bottom term, we're going to factor this, because if you look at the bottom and the top, what's happening is we can see that if you take if you take this and you divide it by 2, you get this. Okay, and the reason we're going to do that will become very clear in a few minutes. So we're going to do, so we're going to do 2 times 0.010 raised to x. And now using the laws of exponents, we're just going to raise both of them to x. So 2 raised to the x times 0.010 raised to x. And now the reason we did this is because we really wanted to cancel out, we really want to kind of cancel out the top term and this part of this term. So see, now we're kind of at the position where we can cancel those two out. And so now this simplifies to 0.5072 is equal to 1 over 2 raised to the power of x. So now we're going to invert this whole equation because we're trying to solve for x, and x is in the denominator. So when we invert this whole equation, we get 1.97 is equal to 2 raised to x. And you can round that 1.97 to 2. So we're going to put 2 is equal to 2 raised to x. Okay, and if you simplifying further, you can see that, well, 2 raised to 1 is equal to 2 raised to x, so x is equal to 1. All right, so therefore we know that this is equal to 1. Now the next step is we have to calculate what is y. Okay, so to calculate y, if we go back to the trial data out here, notice carefully, to calculate x, we chose whatever term had y was raised to y. We chose 2 of the trials where that term was constant. To calculate x, we're going to use 2 of the terms, 2 of the trials where the x term is constant. So it makes sense to use trial 2 and trial 3. Okay, so we already know what trial 2 looks like, which is essentially this one out here. That's trial 2. We're just gonna rewrite trial 2. I'm gonna write trial 2, which is 0.0069 is equal to k times 0.020 x raised to x times 0.010 raised to y. That's trial 2. Trial 3 is going to be, let's go back up here. That's going to be 0.0098. Let's erase that. Okay. That's going to be 0.0098, and then that's 0.020 and 0.020. Okay, so let's write that down. 0.0098 is the rate times rate constant, and then CHCl3 is 0.020. You might want to pause the video out here to just make sure you're following along. Okay, and 0.020 raised to y. And now we're going to divide these two just like we did in the previous step. And when we divide these two, see the k's go away, these two go away, and then essentially the left hand side simplifies to let me see, well, actually let's not simplify that right now. Let's keep that as is. The right hand side, we can do the same trick we did before, where we can write this as 0.010 raised to y over 2 raised to y times 0.010 raised to y. And then the y terms cancel out here, and that is going to give us 1 over 2 raised to y is equal to this. So now, because the y is at the bottom, we're going to flip the entire thing. So if you flip the entire thing, we end up getting 1.42 is equal to 2 raised to y. Okay. All right. So now we have this. Now, in order to solve for y, since we don't have a whole number out here, uh, something that's easily factorable, you want to use the rules of logarithms. Okay. So to use the rules of logarithms, just follow along. So if I take the log of both sides, okay, so I'm just going to write log of 1.42 is equal to log of 2 raised to the y. Then using the rules of logarithms, I can take the y, which is a power, and bring that in front of this log. So multiply it with log of 2. So therefore this becomes y log of 2. Okay. And so now if I want to isolate the y, I write y is equal to, I'm going to take this and I'm going to divide it by this. So that's going to be log of 1.42 divided by log of 2. See if that makes sense. All right. So, and if you simplify that, okay, you will get 0.506, which you can round to 0.5 or 1/2. Now, we have a fractional order out here. So what that means is, while it's not common, it is very possible to have a fractional order for any reaction. So we have to put this. So why is this? So we have to put this back into the rate law. Okay. So if you go back up here, that is the rate law, right? So we have to just rewrite this rate law with the value of x and the value of y. Okay. So we can actually, we can either rewrite it there or we can just rewrite it down here. So rate is equal to k times CHCl3, and the value of x for CHCl3 was 1, which we discovered, which we figured out. And then the value of y for Cl2 is 1/2. So there you have it. So that is the rate law for this reaction. So now the next question is, we have to find the rate constant for the reaction. So to find the rate constant for the reaction, the simple way to do it is just take any one trial, plug the values in, and then solve for k. Okay, so we're just going to go ahead and take trial 1 for this step. So let me just go ahead and number this. So that is for part A, part B. Okay, so we have, so we're going to take for trial 1, it's 0.003. Oops, sorry. 0.0035 is equal to K times the concentration CHCl3, which was 0.010 raised to 1, times Cl2 is 0.010 raised to 1/2. Okay, and so if we're just going to divide both sides by these two terms. So 0.010 raised to 1, 0.010 raised to 1/2, and we'll put the same thing out there. I'm just going to copy that over. Please pause the video and follow along, okay? All right, so once we do that, these two cancel out, okay? And then we have to simplify the left-hand side. And when we simplify the left-hand side, we actually get 3.5. And then now the key thing is to understand what's the unit of this. So the unit to understand is, notice carefully, I'm going to draw that in a different color out here. So the unit for the rate given to us in our problem was what? Molar per second, right? So that's going to be molar per second, okay? Or we can rewrite that as molar second inverse. And then each of these are the concentrations. So that's going to be molar for that one, and then molar for this one. But this one is molar because it's raised to the power of half. So that's going to be molar raised to 1/2, okay? And so if we simplify all those units, we'll actually get, notice carefully, let's just simplify it and show you. So these two will cancel out. So molar 1 to the minus half will actually go on top. So that'll be molar to the half. Okay. So that's molar to the half. But then you still have the second to the negative 1. Okay. All right. Now let's see. This should really be molar. Let me think about this for a second. All right. Okay. So essentially, what's happening out here? This should really be uh, this is molar to the 1/2. My bad. Let me just write that properly. Molar to the 1/2, which ends up being molar to the minus half. So let me go ahead and erase that and write it properly. So molar to the minus half and second to the minus half. So that's 0.00. Sorry, that's 3.5. Okay, so that's the value of the rate constant. Okay, so then the third part of the problem is, what is the overall order of the reaction? So the overall order of the reaction you can find by adding the orders of the individual reactants. Okay, so out here we already know what the rate law is. So we're just going to take the 1 and the 1/2 and add that. So the overall order is equal to 1 plus 1/2, which is 1.5, or you can write this as 1.5. All right. Okay. Well, that was it. I hope that problem made sense. Thank you for watching.